We are in record mode, folks. All right, so we got length 1, we got length 2, and we got length 3. Y equals e to the x minus 1. And this curve right here is y is the cosine of x. The ordered pair is probably an important thing to have. That ordered pair resides at, I think we ended up with 0.601 and 0.825. Okay. Again, where it comes from, the curve length, you have a curve, and you're looking at a particular point on the curve. What you want to consider is this length. We've got a delta x and a delta y. It all comes from the Pythagorean theorem. L is the square root of delta x squared plus delta y squared. Then you multiply by the square root of delta x squared over delta x squared. This denominator, you sneak that into the radical, and what you end up with is length equals the square root of delta x squared over delta x squared plus delta y squared over delta x squared. And then the second piece of that radical we introduced, this guy, we just write that as, well, it's a square root of delta x squared. So the square roots and the squareds cancel each other out. And you have a delta x. And that's the, that would be sort of a Riemann sum to how you would set up the integral. The actual formula, again, coming from the Pythagorean theorem, becomes your curve length is the integral from a to b, the square root of 1 plus, and we're not going to write it as delta y over delta x, we're going to write it as dy dx. And then we're going to square that quantity. Be careful, this is not the second derivative. I think there's the syntax of the second derivative and dy dx squared, they do look very similar. Be advised that this is the derivative squared, not the second derivative. And that's your formula for curve length. Length 1. Okay, we're looking at the integral from, we're going from 0 to 0.601. The square root of 1 plus, okay, let's see, I need that exponent. We're talking about the exponential equation. The derivative of that is just going to be e to the x. The constant of subtracting 1 goes away. So we've got e to the x, that quantity squared dx. And this is a calculator series of questions. So let's engage the calculator for us. And that's what I got for length 1, 1.023. Is anyone not getting that? Okay, let's stick with the pastel colors. And let's get length 2. This is going to, is that too light? Integral, this time we're going length 2. We're going to go from 0.601. I believe that's pi over 2, isn't it? Yeah, this is pi over 2 way down there. So we're going to go from 0. No, not 0, 0.601. 0.601 is our lower bound, to pi over 2 is our upper bound, and it's the square root of 1 plus, okay, I need the derivative of cosine of x. Well, the derivative is the negative sine of x. So I know that technically the negative goes away when we square it, but I'm just going to write it in just because I want to be precise. That quantity squared dx, and I'm getting 1.227. And let's see, L3 is pi over 2. It's 1.7 something. So anyway, in order to get your answer, you want to add this plus that, and you're going to have your perimeter. The perimeter I ended up with, again, whatever the approximation of pi over 2 is, I ended up with a perimeter of 3.871. All right. So hopefully that went well for you as far as perimeters go. Well, actually, as far as curve lengths go. Yeah. All right. Next up, we're going to be talking about surface area. What I've shaded is the surface area of this shape. And the way we're going to go after this thing is we're going to use the curve length in conjunction with a hoop. Imagine that we have a curve. We know what curve length is. We just talked about that using that little Pythagorean theorem. And we've got this tiny little triangle that has a dx horizontally and a dy vertically, and together with the Pythagorean theorem, we've got this little curve length, right? Well, at the bottom of this rotation is the mirror of that curve length, which is down here somewhere. There's the L down there. And that little speck of length, it rotates, it follows the revolution of this shape. Oh, that's terrible. It follows the revolution of the shape, something like that. You can hopefully imagine it's like a ring on a barrel. So what we're looking at, if we want the volume of this thing, the volume is going to be, we've got that length, and that length travels around a circumference. So since we're talking about a volume of revolution, that length travels about a circumference, which is 2 pi r. And hopefully you guys are seeing that the r is defined by the function. This is the r. So in this case, the function, the r, the radius of this piece is defined by the function, the cosine, the y equals the cosine of x. So this is in effect the r equals cosine of x. And the last thing we need is we need the thickness of this little hoop. That's going to be thickness, THK. All right, so ballpark are, oh, and my apologies is, I guess, wait, I shouldn't have written volume there. Hold on. No, I apologize. There is no volume to this. This is the surface area. The surface area, what we've got is we've got the length of this curve, and we're going to take that length and imagine it's like a dab of paint on a brush. We're just going to follow it around the circumference of that shape. Apologies there. So surface area is the curve length times the circumference. So let's get out of theory mode and actually get the surface area of region B. Hopefully you guys can see there are 2 parts to region B. We're going to have to do this in 2 separate integrals. Okay, there is our region B. We'll call this B1, and we'll call this B2. So maybe I should do B2 first, since we've already talked about the radius of this. This is defined by y equals the cosine of x, which in this case, it happens to be the radius is the cosine of x. So our surface area of B2 is going to be the integral. Okay, this bound, recall, is 0.601 to pi over 2. We've got to deal with the circumference of this thing first, which is going to be 2 pi r, which is cosine of x. And now we got to add the curve length component, which is we already just copied this integral from the earlier example we just did. It's the square root of 1 plus negative sine of x, that quantity squared, dx. And it is a rather messy looking thing. I think the biggest trouble with that will be writing it into your calculator and not dropping a parentheses or something like that. So have at it. See if you can get that surface area of part B. I'll set up for B2, the right side. I'll set up for getting the left side. Okay, hopefully your surface area was a value of, let's see, 3.748. No, 3.478. That's what I got as the surface area, the amount of paint it would take to cover up this volume of revolution. That would be square units. Our surface area of the left side, what I called B sub 2. Remember that the equation, this is y equals e to the x minus 1. That happens to be the radius for this. So setting that up, our bounds, we're going from x equals 0 to, let's see, x equals, what was that, 0.601. And again, we'll get 2 pi r, so 2 times pi, and the radius is defined by that function e to the x minus 1. And curve length. Okay, so we got to do the square root of 1 plus the derivative squared, which the derivative of e to the x minus 1 is e to the x. So we've got e to the x quantity squared dx. And that comes out to a value of 2.557. All right, add those together. This one plus that one. And I got the total surface area of shape B rotated around the x-axis, 6.035. All right. Again, I am recording this. If you happen to have received a mistake as far as your calculator, your syntax is off or something like that, and you feel behind, you can rewatch this. As I look at this, I think what I've done on the iPad, I'm checking myself against the answer key I used when I wrote this as a test, and everything I'm doing on the iPad is matching. So I might have made a verbal typo here and there, but what you're seeing on the iPad is sound. All right. Okay. Yeah. I'm just thinking on the clock where we are. Let me go to the last type of abstract application that you guys are going to have to be responsible for, and that would be cross-sectional areas. This is actually harder to draw than the volumes of revolution. Let me go to it's the last page of this. Let's see. And I was very precise in the wording. It seems like I'm talking like a lawyer. I don't write like this normally, but you want to be very precise in how you're defining this. What it's kind of like is, imagine you got a deck of playing cards, you know, and they're all shuffled and they're stacked and you're ready to deal them out. Well, each one of those cards, think about as a cross-sectional area. Now, we've kind of been dealing with that same thing with our volumes of revolution, but all of our cross sections had a circular nature to them. They were discs or washers or cylinders. Okay, well, you can argue whether or not that's circular or how circular it is, but instead of imagining a circular motion that generates the cross section, imagine instead you had this entity and you started slicing it like you would slice Swiss cheese at the deli, right? And and at the deli, the Swiss cheese might be the same dimensions all the way across. Well, what happens if those dimensions change? Um, let's see. Let me see if I can put this in some context here. Um, let's just do number 13. All of these are dealing with region A, which would probably be a good idea if I had region A. What I would like you to try to do is I'd like you to try to draw this, um, but I'd like you to put your XY axis in kind of a three-dimensional perspective look. Okay, here's the X axis, and there's the Y axis. Or if you were to sort of lay it over on its side, here would be the X axis, and this would be the Y axis. Do you see that? And what would region A be doing if it were lying in that sort of a perspective look of the XY plane? Well, it would be coming up, and what I just drew is the exponential portion, and then the trig portion would go back to the y-axis like that, and that's intended to be region A in the XY plane. This is the x-axis. This is the y-axis. Now, instead of being a volume of revolution, this volume is defined by cross-sectional chunks, pieces, like playing cards, all right? And for the first one, these cross sections are squares. So one of the squares might look something like this. There's the base of the square. And then the square is rising out of the XY plane. Something like that. And then it connects, something like that. And there is a single cross-sectional piece of region A as defined by the problem, all right? And hopefully you can imagine there's a whole bunch of these little squares, skinny little squares throughout. And we're just showing you one of them right now, all right? So how are you going to get, notice there's no rotation component in this. What we've got for this is we've got our cross-sectional area. This is the area. And then we have a certain thickness to this. Right, that's this dimension right here. Where do I put it? That's your dx. So in order to get these volumes, what you need is the cross-sectional area. Well, you've got the area times the thickness, and you got two dimensions multiplied by a third dimension, and you end up with 3 dimensions, which is going to be volume. All right. Well, the thickness is easy. That's almost always going to be our dx or our dy, depending on the direction we're looking at these things. And the cross-sectional area, okay, let's read what it's defined as. The cross sections are squares with their bases in the XY plane. So the base of this thing, the side, okay, here's a side here, here's a side there, here's a side, and we've got buried under here is this, it's sort of resting on this one side right here, which I'm trying to write. There it is. Okay, well, what determines that side length? How do we get from here to there? Well, for this particular question, that's defined by the difference between our upper curve, this is the trig curve, minus the lower curve, and this is the exponential curve. So if we were to look at the cross-section of this thing, I'm going to take this one particular piece that we've got, all right, and this distance right here is going to be defined by the cosine of x minus e to the x minus 1. That's going to be the side length. Well, for a square, the area is equal to the side squared. So as we go to integrate this thing, what we're looking at is we're going to integrate from 0 to, I think that's 0.601. The side squared times the thickness. Well, the side squared is, wait a second. There we go. Cosine of x minus, now be careful with your parentheses on here, the quantity e to the x minus 1. That is the side of your square, and if you want its area, you square it. And we're accumulating all these areas with all of those thicknesses over the bounds from 0 to 601. And that is your equation for the volume, cross-sectional volume. Okay, plug that into the calculator and see what you end up with. I got 0.245. You guys okay with that? All right. The cross-sectional square is probably the easiest one. If you take a look at this, there are two more in the offing. Is it offing or offering? It's the same instructions. A solid lies between planes perpendicular to the x-axis and whose cross-sections are defined by region A. We've done the cross-sectional squares. Now, what happens if the cross-sections were semicircles with their bases or diameters in the xy plane? What would that look like? If you think you can go ahead and get the equation, go ahead. I'm going to try to represent it graphically so you can have a look at it. That's our dog barking in the background. I wonder, oh my gosh. There's the xy plane. Our exponential function goes out like that. The trig function looks like that. Now what we're looking at for number 14 are cross sections that are semicircles. Okay, so that's going to look something like that. And they're going to have a certain thickness that goes along with them. Okay. So if we were to look at this thing straight on, this is our cross section, we'd be looking at it like that. And notice that as we start our journey from x equals 0 we've got, that's where the diameter of this is the widest. And then when we finish this up, we're looking at the cross-sectional volume that's defined until, what is that, x equals 0.601, I believe. What a horrible dotted line. X equals, you can't put a ruler to an iPad though, 0.601. Notice that when we reach x equals 0.601, we've got a diameter that's equal to 0. Now, so what we got to do now is we got to find the cross-sectional area of this thing. Okay, well, this is the diameter is all the way across, but we don't calculate the area of a circle with a diameter. We calculate it with the radius. All right, the area of our circle is pi r squared, and our radius is going to be, well, the difference between those two functions, it'll be cosine of x minus parentheses e to the x minus 1. That's our diameter. We got to divide it by 2, and that's going to be our radius. Right? So that's our radius squared. Now, the other thing we got to be careful with is these things are semicircles. So if you were to just plug that right in, you didn't read the question carefully, you would have double the volume you should. This is the area for a circle. For a semicircle, we're going to divide that by 2. So let's just cut right to the integral. For the volume of this shape, we're looking at beginning our journey at x equals 0 and going until x equals 0.601. The cross-sectional area is pi r squared. So again, careful with your syntax on this. We've got the cosine of x minus this quantity e to the x minus 1. There's pi r squared if this were a circle. Do not forget, we're looking at a semicircle, so we'll divide it by 2. And right there, this is our cross-sectional area. All right, last thing we got to tack on is the thickness of this. We'll call that dx. And there you go. Put that into the calculator. What's your volume? I got 0.096. All right. Okay. I'm going to finish with this one. We're at 49. I think I'm going at an unfeverish pace. I hope, I don't know if I'm boring you or whether I'm overwhelming you. I hope I'm somewhere in between. Let's finish up by doing the equilateral triangles. I think the challenge for this is what is the cross-sectional area of an equilateral triangle? See if you can develop that. I'm going to clean up the board so I can reset everything so I can go through it. See how far you can work ahead of me here. Yeah, be advised, just because the last question had cross-sectional semicircles, or even if they had been cross-sectional circles, those aren't the same as volumes of revolution. So you got to read the questions carefully when you're looking at, no, just that's the bottom line. You just got to read the questions carefully. Like before, I'm going to lay this out in a three-dimensional look. We've got our y-axis, we've got our x-axis, we've got the exponential, and we've got the trig function. As a single cross section, now there are an infinite number of little equilateral triangles. There's the base of one of them. All right. Now, this is a matter of more art than science here. You want to make that look like it's sort of in the right perspective with the axes. So it's probably going to look something like that. It's not bad, actually. Now I'm making it too thick. All right, well, thick is good because it does have a thickness to it. Okay, there's a visual of what we're trying to do. And the base, there's a certain rhythm to these. Hopefully you're recognizing that the base of this triangle is the difference between the two functions we've got. The challenge is going to be, what's the height of this guy? That's where you guys are going to earn your paycheck. What's the height? And then, not to be forgotten, we do have a thickness to this. That's what gives us the volume. All right. There's an equilateral triangle. Ugh. It's not much better, but that might be as good as it gets. Let's see. Remember, with an equilateral triangle, these are 60-degree angles. Look at me, calculus teacher talking in degrees. Yeah, 60, 60, 60. This is, if you cut it in half, we've got ourselves a 30, 60, 90 triangle. And the proportions of the sides of a 30, 60, 90 triangle are 1, 2, square root of 3. All right. So let's see here. If this is my base, this distance right here is going to be the base over 2. So I'm going to set up a proportion. Let me rewrite here a little bit. This is base over 2. And this I'm going to call the height. I'm going to set up a proportion that the height over the base over 2 has a ratio that's equal to the square root of 3 over 1. Is that right? Yeah. So our height of this thing, sorry, I'm having a geometry moment here. Our height is equal to square root of 3 times whatever the base is over 2. So there's our height. So our formula for the cross-sectional area of an equilateral triangle is area is 1/2 the base times the height, which is equal to 1/2, okay, whatever our base is, times square root of 3 b over 2. As much as I may have botched that, that proof, I think it is correct. What we end up with is root 3 over 4 base squared. That's your cross-sectional area. All right. So that brings us back to the calculus part. What is the volume of that shape? All right. Well, we're gonna. What color do we want to finish up today? Let's finish up in red. Let's go bold here. We're going to finish this. We're going to start this journey at x equals 0. Let's see if I can make a better dotted line. We're going to better. We're going to finish the journey at x equals 0.601. And we're going to accumulate all of those volumes of all of those triangles. So the volume equals the integral from 0 to 0.601. Root 3 over 4, and now we got to do is we got to square the base. Well, the base, remember, it's going to be defined by the dominant function that defines the base. The upper one, if you will, is the trig function. That's the cosine of x. minus the second function, which it's down here. That's the exponential one. That's e to the x minus 1. Okay, there's our base. We need to square that. And the dx makes the integration engine go. And there you go. You put that to a calculator and get 0.106. All right. Okay. Unless you guys have any questions, I know we're a little bit early here on the clock, but gave you guys a ton of stuff here. If you, let me just pull right out of screen, pen mode, stop share. All right, and there we go. So ton of abstract information there. And I've got at least 3 tests that are written just like that one, have different equations. I think even with these, there was 1 or 2 that we didn't do. I would expect that you'll see one as a practice vehicle probably by next week. I'm trying to keep track of everything we've got to do. You guys have some topic questions that are due today. If you look ahead to the pacing guide, you're going to see that what we have covered over Tuesday, Wednesday, Thursday, and today is about 6 or 8 topics on the MyAP videos. So we've done it. We've compressed a bunch of concepts, a bunch of topics into a brief window of time. Hopefully, it's a curious departure when we spend a lot of time looking at the techniques of integration. You know, recognizing when to use U substitution, when it's going to be a integration by parts, partial fractions, or completing the square, whatever. To going to where you're just using the calculator. You don't care about the integration. It's a matter of seeing what it is you're accumulating. So I don't know. Personally, my personal preference is I like the puzzle component of integrating. Using the calculator and getting these abstract answers to abstract shapes, it lacks a little bit of the meaning for me, but it's still a worthy exercise. I'm going to close out here. I'm trying to think of anything I'm forgetting. As soon as I hang up, I'm going to think of like 3 things to talk to you about. If you guys have anything, let me know. Again, topic questions, watch the videos. You have 1 ebook assignment this week. And don't think that because 8.3 isn't due till next Sunday, it's not a good idea to start on it now. It will take you some time. My version is online as usual, and maybe it won't take as long as I did because I put a lot of time into being a self-sufficient explanation tool for you guys. So hopefully you can follow along. I hope it's a little more than the show me an example that you get from the ebook. It should be standalone as far as the graphics that I put to it, drawing pictures, and the detailed steps that I tried to show. I hope just because the other thing that's kind of curious about it, I'm starting to ramble here a little bit, is if you see that the question asks you for an exact answer, I'm not sure you can do it with a calculator because your calculator is going to give you a decimal answer. And unless you know what fraction that came from, you're going to spend a lot of time reverse engineering what the answer is they're looking for in the ebook assignment. So now the upside is most of those types of questions have very easy bounds for calculation. You'll know what I'm talking about when you get there. Good times happen if you see that they just want an approximation to like the nearest thousandth. Then you know it's a calculator and just press some buttons. Yeah, I'm rambling now. I am assuming that without questions, you guys are good to go. I hope. I will be recording this, so if for some reason an explanation eluded you, you can watch the video or you could just ask me later in class. All right. You guys have yourself a great weekend. Be well. Have fun in the snow. All right. Bye.